Electrochemistry. Let's begin with what electrochemical cells are. Now, during electrochemistry, we're going to use cells that generate electricity. So what we are not doing is providing an external power supply. There's no battery or there's no external cell supplying an electric current. So this is where this differs from electrolysis. We remember electrolysis from GCSE. An external DC power supply was provided to give a positive and a negative electrode. At A level, we use redox reactions that involve the transfer of electrons to provide a potential difference. A redox reaction is where we have both reduction and oxidation occurring. For example, the reaction between zinc and copper sulfate, which is our displacement reaction to get copper and zinc sulfate. So we've got zinc oxidation number 0, copper is +2, and then we end up with copper as a 0 and zinc with a +2. So the zinc has been oxidized and the copper ions have been reduced. This is an example of a redox reaction. So instead of electrons being transferred directly from the zinc to the copper ions, we can build a cell which separates the two different redox reactions. So we know that reduction and oxidation can be represented in half equations. Now each of these half equations are going to be represented as a half cell. So let's take our zinc and our copper sulfate. We are going to use a zinc rod and a solution of zinc sulfate. This is going to be an equilibrium of the ions and the zinc foil or zinc metal electrode. So what could happen? What we have is our zinc atoms can lose electrons to form zinc ions, or we could have our zinc ions gain electrons to form our zinc atoms. So we are setting up an equilibrium. The zinc atoms on the rod can deposit 2 electrons on the rod and move it into the solution as zinc ions. So what this looks like is our zinc can lose 2 electrons to form zinc ions, and these zinc ions then move into solution. The zinc ions that are in solution can gain 2 electrons to form zinc atoms, and the zinc atoms move on to the electrode. In both cases, a potential difference is set up because there is a transfer of electrons. The position of the equilibrium will determine the potential difference between the metal strip and the solution of the metal. So during our reduction reaction, where our zinc ions are gaining 2 electrons, this would result in an accumulation of positive charge on the zinc rod. Whereas in our oxidation reaction, an accumulation of negative charge is on the zinc rod, because our zinc rod is losing 2 electrons, so therefore a negative charge would build up. So if this process was happening, the oxidation, we would have ourselves a negative electrode. if the reduction process was happening, we would have a positive electrode. And this is how we can determine whether we have a positive or a negative electrode. So let's look at these two in more detail. If we look at now copper. So if we look at the oxidation, so oxidation is loss of electrons. So copper electrode, solid metal, in a solution of its ions. So typically we could use copper sulfate. What's this going to do? Lose 2 electrons to form copper 2 plus ions, which are aqueous in the solution, and 2 electrons. So oxidation, we have our loss of electrons. Where the electrons go, they build up or they accumulate on the rod, and the ions move into the solution. So our equilibrium is shifting to the right. So therefore we end up with a negative electrode and a greater concentration of copper 2 plus ions in the solution. During reduction, and reduction is the gaining of electrons, our copper 2 plus ions, which are in solution, gain 2 electrons to produce copper atoms. So what happens here is we had copper 2 plus ions in solution and they are gaining 2 electrons from the electrode. So this now equates to an overall positive charge on the electrode, forming more copper atoms. So what we would see is our electrode becoming fatter or thicker, or our electrode would gain more in mass because we are producing more copper atoms. Similarly, in the oxidation process, we are reducing the amount of copper atoms. So what we would see is the copper electrode would begin to wear away, because some of the copper atoms have moved into solutions as copper ions. This transfer of electrons, either loss or gain of electrons, is providing us with a potential difference, a voltage, a difference in charge. The potential difference that's produced will depend on the following factors: the nature of the ions in the solution, the concentration of the ions in solution, the type of the electrode used, and the temperature. So anything that is going to shift the position of equilibrium will then give us a larger or smaller potential difference. Now, these potential differences have been measured using standard electrode potentials. Normally these have been measured in comparison to a standard hydrogen electrode. So if we're setting up our electrode potential and measuring the potential difference, these values have been measured for us and are often provided to us. Now what we note is that they are all representations of reduction reactions. The more positive our value, the more likely to undergo reduction. Therefore, reduction is gaining of electrons. So this makes it the best oxidizing agent. as an oxidizing agent is itself reduced. An oxidizing agent will oxidize something else, therefore causing something else to lose electrons by it itself gaining electrons. The less positive or the more negative the value, the less likely that it will undergo reduction. So therefore, the weakest oxidizing agent. Now we can combine half equations, one reduction, one oxidation. So let's take our bromine with our sodium ions. Now we're looking at the electrode potential, so both are reduction half equations. Bromine gaining 2 electrons to form 2 bromide ions gives us an E cell value of plus 1.09. The sodium ions gaining an electron to form sodium metal minus 2.71 volts. Now, the more positive, the more likely that that is undergoing reduction. So this will be our reduction equation and this will be our oxidation. So in our reduction equation, this is now going to be the positive electrode. If we refer back to here, what happens when reduction occurs is the gain of electrons causing an overall positive charge on the electrode. And therefore, the half equation of the oxidation reaction is going to become the negative electrode. This will help when we want to set up a diagram. So equilibrium in our reduction reaction is going to shift to the right, whereas our equilibrium in the oxidation reaction is shifting to the left. Let's combine these reactions to write an overall equation. So what we have is Br2 plus 2E minus goes to our 2Br minus. And then we've got the oxidation reaction. So that is our Na. So we've got to flip the equation around the other way to show that it's now oxidation. To write the overall full equation, we need to balance the number of electrons. So our oxidation reaction we need to multiply by 2. Because therefore our number of electrons will balance and therefore cancel out. Combining these equations gives Br2 plus 2Na, and then our arrow, 2 lots of Na plus 2Br minus. We can calculate the overall potential difference, the E cell, of this redox reaction. To calculate the overall E cell, the potential difference that would be red, we do the E cell value of reduction take away the E cell value of oxidation. So our overall electrochemical cell will give a reading of plus 1.09 minus 2.71. So that's 1.09 minus 2.71, giving an overall E cell value of 3.80 volts, positive. So we can also represent electrochemical cells both in diagram form and using this notation. So what we're going to look at first is the notation, and then we're going to look at a number of different examples of the setup of how we would measure these E cell values and electrochemical cells. So our electrochemical cell is going to show us what is happening in our redox reaction. So the single line is a phase boundary. So that's an interface between the electrode and the solution. That's what we call a phase boundary. What we've got with the double line is the salt bridge. We're going to talk in more detail what a salt bridge is, and then we've got another phase boundary. Now, what happens next is anything to the right hand side, that is representing what's getting reduced, so the reduction reaction on the right hand side, and then we've got our left hand side, which would be the oxidation part, whichever gets oxidized. We also put the ions with the highest oxidation number closest to the boundary, the salt bridge. So let's look at where these values are actually measured. So they are measured in comparison to a standard hydrogen electrode. Reason being is that the standard hydrogen electrode is at 0 volts. So everything will be measured in comparison to that because we are comparing something with an E cell value of 0. So what this standard hydrogen electrode looks like. We are bubbling in hydrogen gas. We are using a platinum electrode as it is an electrode that is inert, so it is not going to react. And the solution is our H+ ions. So this is because the half equation is 2H+ plus 2E-, and then we have our H2. Now this is equilibrium. So both of these things are existing. So we use a solution of H+ ions, so typically a dilute acid is used. And we are connecting both of our half cells with a voltmeter. Now we are using a high resistance voltmeter. Having a high resistance means that very little current will flow. It allows our transfer of electrons, but very little current is going to be flowing. There are standard conditions that we need to ensure exist. So, if we are bubbling in a gas, that gas would be at 100 kilopascals pressure. We would also be setting this up at 298 Kelvin, and the concentration of any solution would be 1 mole per decimeter. If any of these conditions change, it will affect the position of equilibrium. So here we are looking at the standard electrode potential of a metal ion half cell. So we are measuring the E cell value of our silver. So we are using silver and silver ions, and we are measuring this in comparison to the standard hydrogen electrode. So what we need to do in terms of the setup is we need to ensure that there is a salt bridge that is present. Now our salt bridge typically is going to be, the salt used is potassium nitrate solution. That's because all nitrates are soluble. So what will happen is that we will always have a soluble salt placed in the salt bridge. What this does is it maintains equilibrium. Now what this means, if this was not potassium nitrate, and let's say for example it was potassium chloride as the salt bridge, because the salt bridge allows the flow of ions, so we check the ions that we're using in our solution, we have silver ions. Now, if we were using a chloride ion salt bridge, this would result in a precipitate of silver chloride. So we do need to have an understanding of our solubility rules. Silver chloride is insoluble, so we would end up with a precipitate of silver chloride, therefore taking out silver ions from our equilibrium, which is what we do not want. We want to maintain equilibrium so that the concentration of the ions remain constant. So therefore we use a nitrate, typically, salt bridge, or any other salt that is not going to result in a precipitate. Now what's going to happen? Let's take a look at the half equations. The half equation for our silver ions, so all of these are the reduction reactions, and then the E cell for the reduction process. What we can see is that we have a more positive silver ion E cell value. So this means that this is going to be the reduction and this is going to be the oxidation reaction or process. So what this looks like is, if we are having reduction, which is always going to be represented on the right hand side, so that is why we put our Ag and Ag plus on the right hand side of our diagram, because this is the side that our reduction process is happening. Therefore this will become the positive electrode and our platinum hydrogen electrode will become the negative electrode due to oxidation. So oxidation is the loss of electrons. So what is happening is we have got a loss of electrons and a gain of electrons. So our electrons are being transferred in this direction. So what's going on is our hydrogen, we have our oxidation process, so that is forming H plus ions and 2E minus. These 2E minus, they are moving through the wire that is connecting the electrodes together. This is resulting in more hydrogen ions going into solution and less hydrogen gas. So what does that mean for the opposite side, the reduction side? What's happening here is our silver ions are gaining electrons because it's reduction. They're being gained from our hydrogen electrode to form silver atoms. So what we would visibly see happening here is our silver electrode becoming much larger or fatter. Increase in size is probably a more scientific way. So our electrode is going to be getting larger on the right hand side. Again, we can calculate the E cell value for this process. So reminder that our E cell is the E of the reduction process minus the E of the oxidation process. So that is plus 0.80 minus 0.0. So therefore we have an overall E cell of our 0.8. Which is exactly what we wanted, because that is what we are using our hydrogen electrode for, to determine the potential difference of the other solution and electrode. So now let's have a look if we have a non-metal ion half cell. So what we mean by this is we are using your standard hydrogen electrode and you are then using a non-metal and non-metal ion as the other half cell. So again, we have our salt bridge, which is a saturated solution of potassium nitrate. We have our high resistance voltmeter. We have our hydrogen gas at 100 kilopascals. We're using our platinum electrode due to it being inert, and we're using a 1 mole per decimeter solution of our dilute acid. Similarly, those conditions will be for our bromine. Our bromine, we're going to be using 100 kilopascals. Platinum electrode, due to it being inert. So because our non-metal in this example that we are doing here is in the aqueous form, we are going to be using a solution of bromine. So we're going to be placing bromine in. So that's why we're using this setup as we have here, as opposed to our metal, because metals are solids at room temperature. So we will be using a physically solid electrode. So the setup looks a little bit different when we're dealing with non-metals. So once again, the right hand side, positive electrode, that's going to be our reduction. Left hand side, negative electrode, that's going to be our oxidation process. We have our two half equations here. We have our reduction and we have our oxidation. Let's see how we would set up a conventional cell representation of this particular half cell. So we start with our salt bridge in the middle. On the right hand side will be the reduction. So we're going to need to put the one with the highest oxidation number closest to the salt bridge. So our reduction process is our Br2 and Br minus. Oxidation number 0, oxidation number minus 1. So closest to the salt bridge is going to be our Br2. Then we put our phase boundary and our Br minus. On the left hand side is our oxidation reaction, of which we have a +1 oxidation number for H plus ions and oxidation number 0 for H2. So then we have our H plus, we have our H2, and because we are using a platinum electrode for both, we are going to show that we are using platinum electrodes. Now, what about if we have an ion-ion half cell? What does this mean? So this means that in one of our half equations, we do not have any solid, liquid or gas. We have both got two lots of aqueous ions. So they are going to be a mixture of solutions, both at 1 mole per decimeter. Again, we are measuring this in comparison to our hydrogen electrode. Let's look at our E cell values. Plus 1.52, therefore this is the positive electrode, that's the reduction process. This is the negative electrode, this is the oxidation process. We're losing electrons, so electrons again are travelling through the wire so that the electrons can be gained by the MnO4 minus ions. And we can see that the electrons are being gained by the MnO4 minus as opposed to the Mn2 plus from the half equation. Let's use these two half equations to write the balanced overall reaction that's happening. So we have our reduction process, and what we're going to do is we're just going to flip the oxidation process around so that it is an oxidation half equation. So we go H2 loses 2 electrons to H, 2H plus and 2E minus. Now what we have to ensure is that the electrons are balanced. We have got 2 electrons and we have got 5 electrons. The only way to balance this is to multiply both equations up. So we are going to multiply by 5 and we are going to multiply by 2. So everything is now getting multiplied by 2. So that gives us 10 electrons, 2 Mn2 plus, that's now giving us 8 H2O. And we're going to multiply this by 5, so that's 5 H2. That gives us 10 H plus, and then we've got our 10 E minus. Now we can combine these two half equations 2MnO4 minus plus 16H plus, the 10E minus, we're just going to put this here for now, and the 5H2. This produces 2Mn2 plus, 8H2O, 10H plus ions, and 10E minus. So what I want us to look at now is what's going to get cancelled out. We've got 10 electrons on the left and 10 electrons on the right. So the electrons cancel. We've got 16H plus on the left and 10H plus on the right. So 10 of the H pluses cancel, leaving us with a net of 6H plus on the left. This leaves our overall reaction to be 2MnO4 minus plus 6H plus 5H2, 2Mn2 plus 8H2O. Now, to understand if a reaction is feasible, will it happen? It will happen if the E cell value that we calculate, reminder, to calculate your E cell, you're doing the E of the reduction half equation minus the E of the oxidation equation. If that overall sum is positive, then yes, our reaction is feasible. So let's take a look. So we are using copper 2 plus, and we're using Cl2 and Cl minus. Let's refer to our table. Cl2 plus 2E minus goes to 2Cl minus, that's a 1.36. So that's a plus 1.36. Remember, that's for the reduction. Then we're going to look at the E for the copper. And the copper is plus 0.34. So again, these are for the reduction processes. So let's write the reduction reactions. That's gaining of electrons. So that's Cu2 plus 2E minus gives us Cu, and that is an E value of plus 0.34. Then we have reduction gaining electrons, so that's Cl2 plus 2E minus gives us our 2Cl minus. And that has an E cell value of plus 1.36. Now, our plus 1.36, that's a higher number, therefore this one is more likely to be reduced, and this is more likely to be oxidized. So if we were to represent this in a diagram, we need to add in our salt bridge to maintain equilibrium, to ensure no precipitates that are going to shift the position of equilibrium. We're using a copper electrode in a solution of copper ions, and that would be at 1 mole per decimetre. We're doing standard conditions. Chlorine is a gas at room temperature, so that's going to be at 100 kPa. And then a solution of chloride ions at 1 mole per decimetre. And because chlorine is a gas, we are using a platinum electrode. So, on the right-hand side, we have reduction. So we put our reduction half cell on the right, our oxidation half cell on the left. So we are going to have our negative electrode, we are going to have our positive electrode, and our electrons transferring from our left to right. Is this feasible? Well, let's calculate our E cell. So that's the E of the reduction process minus E of the oxidation process. So we are doing 1.36 minus 0.34, which is 1.02 volts positive. Yes, it is feasible. So we're going to do two more things here. We are going to represent this as a conventional cell to show you how we would put that together. So start with your salt bridge. To the right hand side is reduction. Closest to the salt bridge goes the higher oxidation number. So that is Cl2. There's a phase boundary because Cl2 is a gas and Cl- are aqueous ions. Again, another phase boundary because the platinum electrode is a solid. On the left hand side is our oxidation process. The oxidation number of copper ions is copper 2+ and copper atoms is 0. So highest oxidation number closest to the salt bridge, they are aqueous. So we need a phase boundary because copper is solid. Lastly, we are going to combine the two half equations to write the overall equation. So we start with our reduction and then our oxidation half equation. So that's Cl2 plus 2E minus goes to 2Cl minus, and Cu loses electrons to form Cu2 plus and 2E minus. Lucky for us, the electrons are already balanced on the left and on the right when we were to combine these. So therefore we end up with Cl2 plus Cu, and we get Cu2 plus ions and 2Cl minus ions.